So next, I'd like to welcome Scotty Cowling, Whiskey Alpha 2, Delta Foxtrot, India.
It's electronic. I can't use it. First, I'd like to start off by thanking Nathaniel and the crew at Case for putting this on and inviting me. It was great. It is great, and still more to come. Also, I'm the vice president of TAPR, who we're working with Nathaniel on some hardware, which I'm going to describe here momentarily. But in September in Detroit, we have the Digital Communications Conference, which is kind of like the digital radio version of this conference. Is there anybody who didn't get one of these? I tried to hand them out. But if you didn't, we'll be happy to give you one. It's pretty close to here, it's just over in Detroit. And it's September 20th to 22nd. Also, down on the sign-in table, there's membership applications if you'd like to support TAPR. We'd love to have you as members. Every one of you. So we take anyone, is that what you're saying? Take anyone's money. We give back massive amounts of goodwill though, so. Yeah. So anyway, I'd like to talk about some real hardware, and this is the turbo mode. I told most people that when I heard it was 15 minutes, it's going to be a movie. So not quite that bad, but every year at HamSCI we have a contest to see who can get through the most slides in the least amount of time. So I'm not sure I'm the winner or not, because when you win, sometimes you get run out on the rail. So anyway, to start off, I have a question for people in the audience. How many Raspberry Pi, everybody knows what a Raspberry Pi is, right? If you don't, out. Okay, how many, we'll issue you one, that's right. It comes with your registration fees, along with dinner. How many people have Raspberry Pi? A Raspberry, okay. How many people have 5 Raspberry Pis? How many people have 10? This is a tough crowd. 15? 15? 20? Come on, now be honest. Okay, put your hand down then if you haven't counted. 22. Okay, now how many are still in the box? So you got 19 really then, with 3 backups. Okay, you still win. How many have none? See me after class. We'll fix you right up. Okay, so let's talk architecture. Not really this kind, but this is the only thing I could figure to put on this slide. So start out this way. The idea here is that TAPR wants to build some hardware that's going to satisfy the space weather station criteria as well as other users, because the bigger base you get, the more you can sell, the cheaper it is, the happier everyone is. And then, oh, it's cheaper, that means you get more users. So more people are happy. So personal space weather station, this is just my wild guess pulled out of nowhere that from right now, from what the specifications that you've heard Tom and John talk about. But just as an example, the idea is that you have a data engine with a separate GPS DO, with a separate receive and transmit, basically socket. So it becomes 4 pieces. And you pick the level of performance you want for each one of these 4 pieces. Because not everybody wants a $150 GPS DO, although maybe everyone wants them now that Rob's told us about how great they are, and probably do. But maybe some people don't. Maybe you want a $20 oscillator instead. So you pick one from the group of oscillators that we have. And this also allows us to focus a lot of attention on the oscillator itself, which, as you may have gathered by now from the last few talks, that's where a lot of the technology needs to be applied. So, and then sensors, these are low speed. These can reside on shields. They can plug into PMOD connectors. They're not really demanding. What's demanding is the path from these 2 guys to whatever processing engine here we have in here, like an FPGA. And that's not shown, but it's just assumed to be high speed, high bandwidth, because that's the main deficiency I see in a lot of SDRs that I look at is they may have tremendous horsepower on the RF side, but you can't get the data into anything to process it. so it becomes not as good as it could be. So then, satellite station may be another application. So you use a LNB down converter and a filter, and you undersample on the receiver, on the transmitter, up convert with the PA to your dish. And guess what? You can maybe be able to use the same data engine programmed differently because it's got an FPGA on it. And you may or may not need a GPSDO. You may just need a high stability TCXO. And you probably will need a client computer. Another application would be just a HF experimenter. So I've tried to color code these in terms of the performance level that you want. So notice that this is now a lighter shade. So it's a premium oscillator maybe, but maybe not a GPSDO. I mean, we've sold lots of HPSDR systems without GPSDOs, although some people want them, so you make it as an option. And then for a low-cost remote radio, you don't even need a PC or a single-board computer. The FPGA can stream the data out right onto the internet, right out to your local network, whatever. And the idea is a low-cost oscillator, maybe 12-bit ADCs and DACs, whatever your performance is that you require. I mean, look around how many RTL SDR dongles there are. They're only 8-bit ADCs, and there's millions of them everywhere. And then if you want a premium performance, I mean, you know those guys that buy Hilberling receivers, right, that get on and listen to WWV. But they listen to it very well. That's right. And like my buddy says, it's because most people buy radios with their eyes and not with their ears. So, what are we actually going to build? This is a great cartoon. Okay, now I want to go through these kind of fast because I don't have very much time, but it is all about trade-offs, and I have slides for each one of these, but I can probably do them all right now and skip over the next 5 slides. But as we know, lower cost is more users. And if you want to get a giant base of networked radios, then you want to make it inexpensive. If it's cost $5,000, you're not going to get near as many people as you're going to get who are willing to spend $200 on the radio, or $50, or $20, or $8.95, right? And this is an 8.95. Okay, capability, I mean, we all know this. You want more, costs more. That's pretty simple. And we already covered that with the cost. Cost and size of the user base are pretty much inversely linked. And adaptability, now the adaptability, everybody says, oh, well, it's going to be too complicated. You're going to have too many versions because you're going to make all these modules come in different flavors. Well, okay, the adaptability is not for you guys. The adaptability is for us building it. So we can say, oh, you've got this application that you want to cover. Well, we can just pick one from A, one from B, one from C, and plug them together and write some firmware, and now you got that application covered. As opposed to having to relay a board out, go through the whole hardware exercise. And expandability and upgradability, kind of what I talked about earlier. So if you're on Space Weather Station, you decide that you want to talk on the satellite because HamSCI just launched their new Phase 4 system, Phase 4 geostationary satellite. Buy a board or two and plug it together and reprogram it. Now you've got a satellite ground station. Boy, that sounded easy, didn't it? Well, anyway. Yeah, I know. So everything's easy to a hardware guy, especially when it's done in software. So TNC2 was $179 in 1985, which is about $420 today. Now, I don't know about you, but in 1985, I was much more willing to spend $179 than I am willing to spend that amount today. But still, you get the idea. The price point somewhere $300 to $500, which I think is kind of where our $500 number came from. Kind of, again, pulled out of the air somewhat, but okay. Okay, we've already covered that. User base, adaptability. And again, this expandability only works to a point. And this reminds me of my first computer I bought was a 286. That dates me, right? Okay. But I got an expandable one. Well, the problem that you don't realize is every time a new motherboard comes out, it requires different memory and a different processor socket. So there's no upgradability. You throw it away. But in our case, we want to try to do this. Okay, so keep the cost below $500. Offer production options that better match the user's application so we can offer configurations that closely match what the users want. get the word out, like you've seen the crowdfunding sites that their goal was 100K and they raised 700K. Why did they do that? Well, because they had a whole bunch of users who wanted their product and who knew about it ahead of time. And if they didn't know about it, they wouldn't have gotten such a great response. So spreading the word is part of what we have to do. And targeting multiple applications increases the volume, which decreases the cost. Okay, that's it. You get that? Sorry. So this is the proposed modular solution. The data engine is in the big box here. I've coded these lines to be green for high speed and kind of brownish orange for low speed. So if we work the architecture right, you'll be able to use existing Arduino shields, existing PMOD boards, existing single board computers, Raspberry Pis or more powerful ones, Odroids, N2. Everybody know what an N2 is? Brand new Odroid coming out, the end of the month. So, and the idea is if you work this right, I mean, this is a massive system, as evidenced by, well, I'm getting ahead of myself. So this is the receiver module connector. This is the transmitter module connector. You're going to have a clock connector. Gigabit Ethernet and USB 3 will be either soldered on the board or not, depending on which version you buy, depending on whether you want that feature or not. So the one without USB is going to be cheaper. But notice that there's 2 gigabit Ethernet ports. On board, you put a gigabit switch, so now you can plug into your network and to the single board computer or your desktop, whichever you want. So this becomes the high-speed pipe for those who want to do the processing over here, as opposed to in the FPGA here. So it solves both problems. Otherwise, you end up getting stuck having to do the processing over here, which is a little bit difficult for people who aren't FPGA experts. And then if you align these connectors physically properly, you could build a single transceive board that plugs into both of them in case you need more IOs for your board. So this is obviously not the hardware. This is an image I stole off the internet, but it shows the kind of the concept I'm thinking of. And for those who know German better than me, I'm probably off base here, but it sounded cool when I did it. So the idea is that the data engine is this board right here. And what not shown are the RF modules, which of course, since this isn't our radio, it doesn't have any, but they would plug in here and probably hang over the side for your connections to antennas and things like that. Then you'd have a way to plug on a top shield above it and a bottom shield below it, and if you use feed-through connectors, you can end up plugging in a single-board computer below the bottom shield, or perhaps a single-board computer in place of the bottom shield. And our shields will be custom shields. A lot of them will have no logic on them at all, just connectors, so that you can take all the low-speed I/O off of the data engine. Because the one thing I didn't want to do was grow the size of the data engine bigger and bigger and bigger to get a bunch of connectors on it, like for PMODs and for I2C and SPI connections, things like that. So you feed all that to a single connector, build a custom shield, which is really inexpensive. That's just an expander, basically. The contact. Am I out of time already? Okay, so let me go through these real quick. You've seen all this. The name I came up with, since we got all these fruity things here, is Orangesicle, because orange is really the next black, right? And we can get orange solder mask, so there you go. Okay, and the idea is that on the first one, we're going to have a large FPGA, 3-port gigabit switch, and that's about it. Digital stuff on the data engine, analog stuff on the RF boards. And again, 2 RF module sockets, oscillator module socket, so you can pick your performance level here, and low and high speed I/O connectors. And if we do this right, we can build a single PC board that will have these additional features that we can just depopulate to make a lower priced version for people who don't need those options. And here is the eye chart of the block diagram for the entry basic level with the optional real-time clock, the clock oscillator here, receive and transmit connectors there. And I think I got about one more slide here. And also, if you end up needing more horsepower, we'll build another DE board with an Altera SoC part on it, or run Linux on it. or maybe we'll use a Xilinx Ultrascale. Pick your poison. We can do it. Anyway, this is kind of the concept I had for the data engine with the modules that plug in, and then if you have a single module, it plugs into both connectors. You can see I'm a great artist, can't you? Missed my calling. This is the block diagram of the clock module, one of them, which has a GPS on it. So you get actually a GPS DO with a jitter reducing buffer here, and you get 4 outputs. And then what you could do is depopulate the expensive part and use the lower cost oscillators, and then you've got an inexpensive board for that's on the same PC board. And this is a phase noise graph of one of the oscillators that we would pick. But you can see this is like minus 60, and this is like minus 162 dBc per hertz. Okay, and then use standard shields. That's another important thing. All of these,